All right, hi there, guys. My name is Wilfrid, and I'm a senior math tutor. So I'll be covering 10 questions today from calculus. They're just basic calculus questions, and I got these problems from OneClass. So if you have any other problems with your calculus homework or your any questions or any struggles with understanding basic calculus theorems and fundamentals, please submit them through OneClass. And also a little backstory, I guess, about me. I graduated from McMaster with a major in biochemistry and a minor in mathematics. So let's begin. Okay, so the first question is, what is the derivative of secant x? So before we even begin to talk about secant x, we want to talk about a rule in deriving equations, okay? So we have the power rule, we have the quotient rule, or the power rule. We also have what we call the chain rule. So let me spread the chain rule. So the chain rule is mostly applied to functions inside of functions, and when you're deriving those kind of functions, and it says that the function of this huge function within a function, to let's say d of x, can be equivalent to the outside function times the inside function, like this. So that's the chain rule. So we're going to be using this rule a lot during the lesson today, and we're going to be using this rule for this first question. Okay. So first of all, we want to state that the secant of x can also be written as 1 over cos x, or cos x to the power of -1. Okay, sure. So now we want to write out our, I guess, convention tools. So d of dx of cos of x -1. So we're going to use our chain rule here, okay? So we have a function within a bigger function, right? So let u equal cos of x, right? And now if we use our chain rule here, we get this, right? So which is du over dx times dy over du. Okay. So we got u to the power of -1, and dy is just cos x. Okay, so we're going to solve this later. Sorry, give me a second. So we're just going to sub u in. Sorry, I didn't mean to do that right now. So we'll get d of dx of u minus 1. Okay, and then if we use our power rule here, right? So our power rule suggests that we take the exponent down, and then we subtract the power by 1. So we get -1 times u to the power of -2 times du over dx. Okay, cool. And then we want to plug in back our u's. So we have a u here, so that's going to be cos x to the power of -2, and then d of dx of cos of x. All right, and then the final rule is that we know that the derivative of cos x is -sine x. So plugging that all in together, so this is just an aside. Let me just drop a box around this. So plugging this all in together, we got negative cos x of -2 times sine of x, -sine x. Okay, so this is what we get for our derivative. If we want to simplify this, we get sine of x over cos squared x, and we can also write it as 1 over cos x times sine x over cos x. And sine x over cos x is just tan x, so we get, and 1 over cos x is secant x, so we just get secant x times tan x as our final answer. So the derivative of secant x is secant x tan x, okay? So the junior tutor also used the solution that I used. So they used the chain rule, they subbed in u to be equal to cos, and then they used the chain rule like this. And then they derived u, and then they subbed back u in and derived the cos. And then they simplified everything together to get secant x tan x. So solution is correct. Cool. All right, moving on to question number 2. So now we're talking about integrals. So the question reads, how do you integrate sine 2x dx? Okay. So let's just write this down here. So let's say we have the integral of sine 2x in terms of dx, right? So let's say that u equals 2x. So you can see here again, we have a function within a function again. So we want to simplify this function and be able to derive it in a more simpler way and then sub back in our values. So let's say that u equals 2x, right? Let's derive du of dx, okay? So du of dx would equal 2, okay? So then let's say that we can treat these as different variables. So let's isolate for du. So du would equal 2 times dx. So we're going to sub in, and we're going to isolate for dx too. So isolate for dx, which is du over 2. Okay, so we're going to use 1 and 2, and we're going to sub this into our integral. Okay, so sub 1 and 2 into integral. If we sub 1 and 2 into the integral, we get the integral of sine of u and du over 2. We can take out this 1 over 2 constant within the integral to get sine of u du. And now we have transformed our integral in terms of x to integral in terms of u. And now we can simply do this integral because we know what the integral of sine is. And the integral of sine is negative cos. So it's going to be negative cos u plus c. Okay. And then we're just going to sub back in our u here, which is 2x, to get 1 over 2 negative cos 2x plus c. So this is the answer to integrating sine of 2x in terms of x. And we use a substitution method to simplify our integral. And by simplifying it, we're able to find integral easily. And then we just sub back in our u. And then this is what we got. And c is a constant. So whenever you're integrating, you always have to include a constant because you have to assume that there might be a constant when you're integrating. So the junior tutor did the same solution. They used substitution to simplify the integral. And by using substitution, they were able to find it. And then they substituted back u, and they solved. And they found our integral. Cool. All right. Let's move along to question number 3. All right, so question number 3 reads, what is the derivative of e to the power negative x? So we're still going to use our chain rule here. Okay, so as I said before, our chain rule is dy over dx equals dy over du times du over dx. So last time I kind of wrote it in the wrong way. That's why I was confused. But this is how you read it. So we're going to use our chain rule here, and we're going to use substitution to simplify and to derive e of negative x, okay? So let's write it out here. So d of dx of e to the power of negative x, what is that equal to? Well, let's say let y equal sorry, so I meant to say let u equal negative x, okay? So that our function here is now e to the u, okay? So now that we're applying the chain rule, this would be equal to dy of du. So now our dy is e of u, and our du of dx, so our u is negative x, so it's times d of dx of negative x, okay? So you see here that we broke up our function within a function by using u as I guess a placement variable for now, okay? And now that we have this, we can solve this easily. So this equals, so d of du of eu just equals eu, and d of dx of negative x is just negative 1, okay? So now we have negative e to the power of u, and we're going to sub back in our u here, so sub u in, sub int in, and we get negative e of negative x. So the derivative of e to the power of negative x is negative e to the negative x, and we used our chain rule to find this derivative. Okay, so the junior tutor also did this solution. They use a placement variable u, and then they use the chain rule to break down our function within a function. And then they used the power rule and everything, and they came up with our solution here. So the solution is correct. Okay. All right, so question number 4. What is the derivative of ln x? So this is a proof on how to derive ln x. And so the junior tutor provided a proof on how to do it. I'm going to provide a different one, and then I'll run through what the junior tutor did, okay? All right, so we're going to assume that we know, or that we already have proved that the derivative of e to the x is just e to the x, okay? So we're gonna assume that we already know that. So let's say that d to the dx of x, we know what that is, that equals to 1, right? Well, we also know that x can be written as e ln of x, right? So let's write this x as this. So d dx e ln of x. All right, that still equals 1, okay, because this is equivalent to x, okay? So this is technically a chain rule, right? And we know that the derivative of e to the x, or e to whatever function of the power, is equal to just e to the whatever power, right? So if we use our chain rule here, we'll get e to the ln x. And now we need to derive the inside function, right? Which is going to be ln x equals 1. But we also know that e to the ln x equals x. So this also equals e to the ln x equals x, and we have x times dx ln x equals 1. And if we isolate for this whole term here, we get d to the dx ln x equals 1 over x. Okay, so that's how you can derive ln of x, and this is the proof for it. So this is the proof. So the second proof, I'll run through what the junior tutor wrote. So let's start here. So they first said, okay, so y equals ln x, okay? And they're also using the same assumptions that we know, that you know that the derivative of e to the x is just e to the x, okay? So they said, okay, let's say y equals ln x, okay? Well, we can apply e to both sides. So e to the y equals e ln x. And they recognize that e ln x is just x. So they have e to the power of y equals x, okay? Now they're going to differentiate both sides. They're going to implicitly differentiate both sides. So that's should be x. So d to d dx ey equals d and dx of x. Okay, they're going to differentiate both sides. Well, so if they implicitly differentiate, this is a chain rule again, right? So it's going to be e to the power of y times dy over dx, or y prime, I guess you can say, right? Because that's going to be the derivative of y. And here, you don't really need to implicitly derive because d to the dx of x just equals 1. Okay, so now they have dy over dx equals 1 over ey. But they notice that 1 over ey is just e to the ln x, or ey actually just equals x. So they're going to say this equals just x, right? And dy over dx can be alternatively written as d of dx ln x, because they just took this y, they noticed that we can actually derive y, which is just ln x, and now we have proved that the derivative of ln x equals 1x in 2 different ways. Okay, there you go. So this proof is correct. Cool. All right, let's move on to question number 5. So question number 5 reads, what is the limit as x approaches infinity of e to the x, of function e to the x, okay? So they're basically asking us if we write it in conventional notation, what is the limit? So this is the limits notation when x approaches infinity of our function e to the x. So essentially they want to know, the question is asking us for the end behavior of this function as x approaches infinity. So if you were to graph this out, right? E to the x kind of looks like, I'm just going to draw it like this. E to x kind of looks like that, right? So they want to know what happens when x approaches infinity, right? What is the value of our function as x approaches infinity, right? So there's a lot of different strategies calculating limits. You can use conjugates, you can use algebra, you can also use some logic to figure out the limit. But the most simplest method of figuring out a limit is to just plug in the value that it's approaching to. So in this case, when we're calculating the limit of e to the x is approaching infinity, so we're going to say, we're just going to plug in e to the infinity. And infinity is just a huge positive number, right? And since we know e will always be positive because it's a positive base, we know that anything to the power of a huge big number is going to be pretty big itself. So we're just going to say it's a pretty big number, which is infinity, right? So the most simplest method of calculating limits is just by plugging in whatever the limit, the approaching number value is, right? And in this case, as we substitute infinity into our function, we get infinity. So now we know that the limit approaches infinity, the function approaches infinity as x approaches infinity, okay? So the junior tutor also provided that kind of solution. They didn't give the graph, but they reasoned that Euler's number is 2.71828, blah, 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 which is always going to be positive, right? And a number that, a positive number to the power of another positive number is always going to be positive. So the reason that, okay, this exponent is going to be really huge, the value of this exponent is going to be really huge, so we're just going to say it's infinity, and that's why we know that this function, as x approaches infinity, is going to be infinity. So the solution is correct. Cool. All right, question number 6. So they're asking us, what is the integral of negative e to negative x? Okay. So let's write that out. So we are looking for the indefinite integral of negative e to the power of negative x in terms of dx. Okay. So we're going to use our substitution method here to simplify our integral again. So let's say let u equal negative x. Okay. So that means du of dx equals -1, right? And that means that dx equals negative du. So we can rewrite this integral as negative e to the power of negative u, to the power of u, to the power of u, and we know that this will be -1, dx equals -1 times du, okay? So we know that this negative and this negative cancel out. So we have e to the u of du, all right? And we know that the derivative, or the integral of e to the u is just e to the u plus c, right? And we sub back in u here, which is -x. So e to the -x plus c. So this is our integral, e to the -x plus c. So by using substitution, we simplified our integral again so we can easily solve it, and then we sub back in u. Okay. All right, so how do you convert r to the power of 2 cos? Wait, sorry, this should be not like this. There should be cos here. There you go. All right, so r squared times cos 2 theta equal 1 into Cartesian form. Okay, so we have to remember our double angle identities here. So we know that cos of 2 theta equals cos squared theta minus sine squared theta, okay? So we'll have to use this double angle identity to solve this problem, right? So r squared cos 2 theta can be written as r squared times cos squared theta minus sine squared theta, okay? Equals 1, okay? We're going to expand this. This equals r squared cos squared theta minus r squared sine squared theta. Okay, cool. And we can alternatively write this r squared cos squared as r cos theta minus, should be squared, minus r sine theta squared. All right, cool. Now we're going to need to talk about Cartesian form and polar form, right? So currently this equation is written in polar coordinates, all right? So we had, I guess, 2 different coordinate systems. So this is our Cartesian, and this is our polar. So the polar coordinates uses the magnitude of the hypotenuse and the angle as coordinates, and the Cartesian uses its x and y coordinates to graph onto the plane, I guess, or to graph onto our axes, right? So the conversion between Cartesian to polar is, so we have to calculate r, and r is the square root of x squared plus y squared, and our theta value, our angle, is the inverse of tan of y over x, okay? So these 2 equations or formulas will help convert our x and y coordinates into our polar coordinates of r theta, okay? So if we're going backwards, back to Cartesian coordinates, we have to know that x equals r cos theta and y equals r sine theta, okay? And these two equations will convert our r and thetas back into its xy coordinates. So x and y are our Cartesian plane, okay? So I shouldn't have drawn it right in front of my solution here. Maybe I can move it somewhere else. Okay, try moving this like down here. Okay. And I'll rewrite it later. But okay, so we have our equations here: x equals r cos theta and y equals r sine theta, right? Here we have r cos theta, right? So we can say that that equals x squared, and we have r sine theta as y, so y minus y squared. So now we have converted r squared cos 2 theta back into its polar or Cartesian form, which is x squared minus y squared. So this equals to 1, and now we have x squared minus 1 y squared equals 1 is the Cartesian form. Okay, so we have converted our polar coordinates back into Cartesian, or rectangular coordinates, I guess you can say. So the junior tutor also used the solution that I used. They used a double angle identity to transform this equation, and then they expanded, and then they realized, oh, this equals to x and this equals to y, so we'll just sub it back in, and we get our derived equation. So cool. All right. Question number 8. All right, so the question reads, how do you integrate 3 to the power of x? Okay. So before we even begin this problem, we have to recognize a simple fact here. So if a is a positive number, and x is any real number, we can write a to the power of x as ex ln of a, okay? So this is a fundamental fact, and we're going to be using this to integrate 3 to the power of x, okay? So let's write down our integral here. So integral of 3 to the power of x of d of x can also be written as, if using this fundamental fact here, the integral of e to the x ln of 3, okay? Dx. All right, so now we're going to use our, I guess, placement variable for now. So we know that the integral of e to the u is just e to the u plus a constant. So let's say that we'll let u equal x to ln 3, right? If we derive du to dx, what do we get? We get ln 3, okay? And if we isolate for d of x, we get ln 3 du. Okay, cool. So we're going to sub u into our original equation here. So if we sub in u here and we sub in dx, we get e to the u times ln 3 du. Okay, if we can take out this constant ln 3, and all we're left with is eu du. And this equals to ln 3 of eu plus c. And if we sub back in our u here, we get we get ln 3 of e to the power of x ln 3 plus c. And we know that e to the x ln 3 is just 3 to the x, so we get ln 3 times 3 to the x plus c. I think I did something wrong here. Yeah, when I isolate it for dx, this shouldn't be this. This should be It should be dx equals 1 over ln 3. That's why. So as 1 over ln 3, we get 1, 1, 1, 1. So this actually equals 3 to the power of x over ln 3 plus c. Okay, cool. So that's how you derive, or that's how you integrate through the power of x. We use a substitution variable again to simplify our integral, and then after we solve the integral, we just sub back in our variable, our substitute variable. That's what the junior tutor also did. Yeah, cool. So substitution. All right, moving on to question number 9. All right, so question number 9 reads, what is the limit as x approaches infinity of sine of x? So the junior tutor reasons that the sine function is an oscillating function, right? If you graphed it out, its range will be between -1 to 1, right? So as the function approaches infinity, it does not approach a single value. Thus, its limit does not exist. So this is technically true, and the junior tutor is correct. So I'm going to use a different method of describing what the junior tutor wrote out here, okay? All right, so we're going to talk about the squeeze theorem again. So the squeeze theorem suggests that, let's say that we have a function f of x, okay? So if we can sandwich or squeeze this function between two other functions, let's say g of x and h of x, okay? And if the limit of h of x as x approaches, I guess, a number, let's say as x approaches infinity, for example, equals L, and also the limit of as x approaches infinity of g of x also equals L, then we know that f of x, that the limit of f of x, the limit of f of x as x approaches infinity also equals L. So this is what the squeeze theorem suggests, is also called the sandwich theorem, okay? So we're going to use this theorem to try to find the limit of sine x, okay? So if the limit as x approaches infinity of h of x and the limit of g of x as x approaches infinity do not equal the same number, that means that the limit does not exist for this one. Okay, well, yeah. So we have our function, which is sine of x, okay? And we're going to fit it between our functions. Let me make this more neat here. So we have our function sine of x here, okay? So let's say that, let's fit it between these two functions, g of x, and let's say h of x, okay? So what are our functions? What can our functions be? Well, let's say that g of x equals 1, and h of x equals -1, okay? So these two functions fit between our squeeze or sandwich sine of x, right? Because we always know that sine of x is, the range of it is between 1 and -1, right? The values. So therefore, we have -1 here, sine of x, and we have 1 over here, okay? So this is what our junior tutor is proposing, right? That sine of x, the range of it is always between 1 and -1, all right? So if we calculate the limit as x approaches infinity of -1 and the limit of x approaches infinity of 1, we get this. So of -1 is going to be -1. And the limit as x approaches infinity of 1 equals 1. So therefore, these limits, these do not equal the same. Sine of x does not have a limit. Okay, that's another way we can reason that sine of x does not have a limit as x approaches infinity. Okay. Yeah. So since the function is always oscillating, it's not going to approach a single number. It's going to go up and it's going to go down. It's always going to go up and it's always going to go down. And using our squeeze theorem method, we kind of figure that out, right? So yeah. So the solution is correct. Okay. All right, let's solve our last question of the day. The last question reads, find the derivative of ln x squared, okay? So we're also going to use a chain rule again, but this time I'm not going to bring us through step by step, okay? So let's say that y equals ln of x squared, okay? So y prime of x would be the outside function, derivative outside function, right? So it's 2 of ln x. Make sure you use your power rule. 2 minus 1 is just 1, right? And the derivative inside function. So we know the derivative of ln x is just 1 over x. And that equals 2 ln x over x. So that's the derivative of ln x squared. So the junior tutor uses chain rule too. And they describe saying, when using chain rule, always start with the derivative of the whole, then get the derivative of the expression within the parentheses until there are no more variables within to differentiate. So this is technically a chain rule of a chain rule of a chain rule, because there's one function here, which is the ln x squared, then there's ln x, and then there's x within there, right? But since the derivative of x is 1, we didn't include 1 here, but this is a chain rule of a chain rule. So we want to do a chain rule of these first two functions and the chain rule of the two inside functions, okay? So chain rules can be infinite. They can have a function within a function within a function. And even though it's very boring to do that, they do exist, and they're very tedious to do. So this solution is correct. Cool. All right, so that wraps up today's lesson. It was a little bit of a shorter lesson, but I covered a lot of the basics of, I guess, derivatives and integrals, and talked about using the chain rule at length. So next time, if you have any questions surrounding calculus, please submit them through OneClass, and I'll see you guys later.